All right, so thanks for having us here today. So today we're going to talk about deploying Haskell in a microservice environment, primarily written in Python to start with, and a little bit about our robots. So also, if you came to talk about like functors and monads, I'm sorry, this is not the talk for you. This is like an industry retrospective, so I hate to disappoint. Yeah, so a little bit about us. So my name is Jeff Ciesielski. I'm the director of control systems engineering at Kimi. So my background is actually in embedded systems engineering, so like working on custom ASICs and writing C that runs on microcontrollers. So about as far from Haskell as you could possibly get in your career. I'm the rare cat dad of three, and I'm a huge gearhead. So like I've actually managed to turn like working on cars and rebuilding engines into a successful robotics career.
And I am Lianne. I have a history of functional programming. I did my graduate research doing a Haskell to System Verilog project that I actually talked about in front of the Haskell group. I'm a knitting extraordinaire and a big dog lover.
All right, so just talk about what Kimi is for a second. So we're a startup based here in New York. So if you haven't seen our kiosk, you're going to find us in like Bed Bath & Beyond or 7-Eleven. And we basically designed and operate a fleet of robotic kiosks that duplicate keys. So we've manufactured about 3,000 of them to date. We've deployed most of those out to the field. And what we do is we use machine learning and computer vision to classify and measure keys. So when you put your key in, we've got a bunch of cameras that build a 3D model of it. And then we use computer vision assisted CNC to duplicate most common household keys. So for those of you who aren't familiar with CNC, this is computer numerical control. So this is a way of synchronizing a bunch of like stepper motors to work together. And you'd see this used in machine shops and like mills and lathes and things like that. And so we can do most common house keys like on site. And if we can't duplicate on site, we can actually we take all these images, we can upload them, classify them, and duplicate them in our fulfillment center here in New York. We can also do like car keys, RFID fobs, double-sided keys, so just about anything you could imagine. Um, and our team specifically develops the software that drives these robotics, and we write all the like systems level code that like other teams will use to drive their stuff. So this could be like LEDs, cameras, fingerprint scanners, just like a whole litany of USB devices. But then we're also responsible for actually like correcting for calibration drift and actually writing all the manufacturing software for the kiosks. And what's really cool about our job is that the output of our code is actually a physical object. Like we say, we run a script and it actually produces a physical key. But what's weird about that is that when things go wrong, it's really difficult to understand what went wrong because I can't just look at like a debug log that like there could have been like machine errors. And so it's not always clear what happened, and so we have to write really robust code, and it needs to work in like all situations. Like people that you might run on a cluster of a bunch of servers, but imagine like if one of those servers got finicky and like one of its motors slipped and suddenly the whole thing broke down. It's really a complicated domain. And so Lianne and I joined Kimi about like 3 years ago, and when we joined, I think a lot of people that have come into a startup at that point, they're going to suffer the same things we did. So we came in, a lot of the people that had written the original code like weren't there anymore. There was almost no testing, there was zero documentation. And we inherited this what we call like a micro-monolith, right? So it was conceptualized as a bunch of Python microservices using 0MQ to talk, but like if one of them broke, it took down the whole system. So it wasn't very well segregated. And a lot of the problems we ran into, some of them were self-inflicted, but some were also just because we were working in a very large code base in Python. And so it's a dynamic programming language, and people like to get clever, and they would do weird stuff like all this crazy meta programming where they're just adding attributes, and everything's like stringly typed everywhere. We also leaned into JSON really hard. So JSON was our serialization that went back and forth across our IPC system, and also it was how we did configuration. A lot of this ended up very deeply nested, but that's how we ended up sharing data between all of our different systems. Also, it's an imperative language. People use a lot of like side effects in their code, and also our group used a lot of global state, unfortunately, at the very beginning. And that was complicated for a lot of reasons. So we're heavily concurrent. Every process typically has 3 to 5 threads, and it wasn't always properly locked. And so this would also lead to problems where then like testing and mocking parts of the system were basically impossible, right? When you have a system like that, you can't mock something because you run 2 tests in a row and you're going to get different results. And even, one of the worst sins that was committed was like you would import a library module from our standard library, and it would be effectful, so it could touch something on the file system or dynamically monkey patch something in. It was really scary. And then finally, not that it's news, but Python's interpreted, so like anything we didn't test was suspect. We couldn't actually count on it actually working, and a typo could bring us down. And so our team got together after kind of inheriting this monster, and we were talking about what our takeaways were and how we might improve it. And so basically, what we came down to is that we had really unclear interfaces. So we had we have all these messages shooting between different processes, and they're really unclear, and in some cases quite complex. Cutting a key is a really broad domain. And if you didn't understand the entire system all the way through, you were almost guaranteed to get some sort of runtime error from the JSON. We also had very few tests. So the global mutable state, like I talked about, made it really hard to write tests. And then also, we're running this on real hardware. And so you can't reproduce hardware edge cases on demand. I wish I could. That would make my job a lot easier. But we also at the time didn't have simulation. Thankfully, we do now. Leanne wrote a really great simulator. But if I wanted to say like run a test and try to test for 4 or 5 different keys to see if it worked properly, at the time we started, cutting a key took about 3 minutes. So that was like a one-line change would be like a 15 to 30 minute investment in me testing things. And so you multiply that out by a typical like productive software engineer, and that became very onerous. And so what this led to was working code that we just didn't touch. We had tens of thousands of lines of code, and if we wanted to add a feature, a lot of times we would see if we could come at it from like a side vector to kind of add something in, rather than making changes to the core software. Because anything we would change at that point in our startup's life meant that we would potentially lose a sale. And if we lost a sale, that lose enough sales, and I'm not getting paid anymore. And I really like getting paid for my work. And so we kind of got together and we said, how do we fix this? And so a lot of us had backgrounds in compiled languages. So like I said, my background is mostly in C. Lianne had Haskell experience. We had some folks with OCaml experience. And we got together and said, okay, what are we going to do to push this company forward and push our teams forward in a way that's not going to make us want to rip our hair out? And so I'm going to go ahead and turn over to Lianne to talk about the technical parts of this, because she knows a lot more about Haskell than I do.
Okay, so like we talked about, our solution was to have a new language. Not a surprise. So the one advantage to having the microservice infrastructure was that we could substitute subsystems with a new language, and it would just work within the system with just the IPC system. But the new problem was, how do we integrate a new process in? When we have libraries, we didn't want to duplicate library code because that's just a bad idea all around. And we also didn't want to do that because it's time consuming and produces errors, but we still wanted to use that because we can't change our whole code base. And then we needed a way. We have what we call canaries for good reason. They're if they die, then there's something bad happening. We have 50 machines that we just put with beginning software, and we can't just roll out to 3,000 machines new software that we're like pretty sure will work. But so we wanted a way to do this by running the old software and the new software in the field at the same time. And previously we have been running Python, which you just deploy by putting the code on the machine and run. Now we had binaries to deal with. We need to make it in a secure environment and deploy it. So here is a subset of our architecture. Everything is its own process in this beautiful large, and this is just a subset of our whole infrastructure. So we have orders come in, and then per order they get sent to the cutter, which cuts a key, talking to our I/O, our very well named process I/O, and motion that are the ones that actually control the motors. And then we have this AutoCal, which calibrates based on the output of every single cut. And this isn't even including our credit, or it does have a credit card reader, the RFID reader, the fingerprint reader, and all of our cameras, which we have 6, I believe 7 on the machine. So it's pretty complex, and not something we could change overnight. So the way that we decided to do the integration was we built basically this Python edge point. So it was still Python, just sitting there, that would talk the IPC system to the rest of the processes and forward all that information to what we called our core, or the new process in whatever language we had decided on. And we were able to call Python from the other process by sending JSON. Luckily, Python is dynamic because we could just send it a string with the module and the functions and keyword arguments, and it would be able to apply that and then return the result. Did you have a question? Oh, sorry. Yeah, and so basically worked all of our other Python processes over our ZMQ. We had the Python edge point, and then we had a Unix socket that could talk to any new language. This allowed us to bring up, I think we ended up 6 prototypes that could talk to the edge point. Only 2 or 3 had any significant behavior, but it allowed us to really explore without having to rewrite a lot of code. So how do we get to Haskell? First, we started with Rust, which I think is a pretty reasonable. It's known as being a systems language, and it's very type safe. We had a lot of trouble prototyping. The borrow checker with the concurrency at the time was not our friend. And we also have to think about bringing new people on board, because we have new developers that we needed to have working on this code too. So it was just not a good fit. Then we moved on to NIM. Jeff actually has a history. He worked part of the libraries on the NIM. It is type safe, but it looks a lot like Python, so that fit better with bringing people up to speed. We actually basically finished this prototype. We were like 2 features away from finishing it, and we had problems with the garbage collector, and then they didn't really have the concurrency primitives that we really needed to do what we had, and I did not want to reinvent those, because it turns out that concurrency primitives are very difficult to do right. Yeah, so after we basically finished a whole prototype, we made a list of things like, what do we want really? If we're gonna start over, we have to do this the right way this time. We wanted a strongly statically typed language. We really wanted a compiler. We wanted established libraries, so we didn't run into the same problem. So, and we wanted a big base where we can look up problems that we're having, and we could potentially hire new developers in the future. So we ended up with 3 different languages at the end. It was Haskell, that was my language, so I won. OCaml and Crystal. Crystal is a compiled Ruby language that has pretty nice, but it was also new, and we were worried that although it had concurrency, unlike NIM, but there were probably going to be other problems in the future since it was such a new language. Even though we could have Ruby developers, so there was that kind of availability. Next, to kick the bucket was OCaml, which hit some people on our team very hard. It was very nice language, but it didn't have a fully featured serial library, and the process that we were trying to replace talked directly to our microcontroller over a serial port, so that was non-negotiable. And the build system was a little much for us, going from running just code on the computer to setting this whole system up. So, like I said, I won. Haskell wins. So we decided to do Haskell, and it was everything we dreamed it would be, at least for me. So we were able to use ASON to support automatic JSON conversion. So when we send our IPCs, we could automatically detype those, and if there was a type error, it was very clear what it was, or missing messages. And the best part about that was that we could actually define what we called our handlers with the types that we were expecting. It's crazy, I know. But Python didn't have that, especially when you were just importing a dictionary. You didn't even know how many arguments you were expecting. And so that was a big thing, and I think it helps bring in new people. They understand what's happening. And so basically we went, on the left is our old infrastructure. I don't know if you could call it like architecture. It was just a giant loop that talked to another giant loop. And occasionally, most of this stuff was independent, so it was really annoying because you would touch one thing and something that should not have been changed. And that's, on the right, is our beautiful Haskell infrastructure, where every single module that didn't need to know about other modules doesn't. We have, we call it XBVC. That was an internal library that we worked on to generate the messages between the C and the Haskell. And yeah, kind of back to Jeff.
A lot of work went into this, and so I just wanted to kind of like just retrospectively like what went wrong for us, right? Either during like development or during deployment, because this was like a little over a year that we spent like prototyping and finally like settling on Haskell, and so really it was surprisingly few. This went way smoother than I would have guessed. I think the things that bit us during development were like compilation's a little slow. Um, and I don't think that's news to most people who work with Haskell. Like a fresh build, can sometimes take 20, 30 minutes in really big projects. But bringing a bunch of people who, in some cases, hadn't really ever worked in compiled languages on board was really frustrating for them. And so, like, just the speed of development was kind of a problem. But it wasn't too bad. I mean, incremental builds are fine. Learning new tools. So again, with Python, you're basically using either apt or pip. And with Haskell, it was a little muddier. So we ended up going with Cabal, and we got everything set up after a little bit of pain because not realizing you should probably use a sandbox and nuking my own machine like twice because I couldn't get everything fixed. We ended up getting everything sorted out, and we actually ended up building a really nice, or at least I think it's really nice, Docker-based build system around it. So it's it's a single make file. You type make, and it actually spins up a Docker instance in the background, builds everything in isolation, and then kind of just dumps the binaries out, which also allowed us to have an exactly identical infrastructure to what we're running on our kiosk. So we don't have if you're running on a Mac or whatever, you can actually build still. And we may actually switch to Stack in the near future. It seems like the community is going that way. It's just been kind of like low payoff for us right now. So when we get around to it, we will. And then I think one of the biggest things for myself, at least, was getting over the sort of like pure hump. When you come from languages that'll let you do anything, especially C, which doesn't care what you do, it doesn't have any sort of safety at all. Kind of like getting into the idea that like being like functionally pure and like really enforcing that was a little rough. But I think once after about a week or so of playing around with it and kind of realizing the patterns that people use, it was actually quite nice. But the big thing that really bit us, and it actually almost tanked the project, was excessive memory use for us. So like Lianne pointed out, we have a lot of processes running, and all these processes run like 24/7. So we never shut them down if we can help it. And so we ended up having a really bad thunk leak in a serial packet accumulator. I didn't know what a thunk was. I had to look it up. I was like on Stack Overflow forever. And basically, we track how many serial packets we encode and decode. And there's a lot of serial traffic on our machine. And so we had this thunk, like it's obvious to me now, but we had this thunk leak where I was basically saying like failed to decode +1 forever. And then we never had a decode error because our code is awesome, and that actually ended up tanking it. I will note as an aside though that our process was killed after consuming like 400 megabytes of memory because the machine learning team complained that they didn't have more than the 3 gigs they were already consuming. So it just doesn't seem fair. So that was a pretty easy fix. We marked the inputs as strict to that, and that took care of most of the issue. I will talk a little bit more about that on the next slide though, because there were some other things about that were problematic. But we spent several days tracking on other thunk and space leaks. Despite our best efforts, and we were using the profiling tools, we were using as many debugging tools as we could. We couldn't seem to close everything off. And looking around on Stack Overflow and on various forums, it seemed like some folks had run into similar issues. Like if you use O2 versus O0, that will actually tail call optimize in ways that you would sort of expect Haskell to, but if you use O0, it actually doesn't. So things like that fixed some of the problems, but not all, and we couldn't ever really squash them all. And so I'm really scared to say this in front of a mostly Haskell audience, but we actually went the nuclear option, and for us, laziness is opt-in. So we've set strict by default, we've locked everything down, it kind of goes against a lot of what makes Haskell really awesome in some ways. But when we're onboarding new developers, and there's just a ton of cognitive load for doing code reviews, I don't have to think about like, is this going to accumulate over time? It just tends to work for us. That's bit us twice, I think, where we did have a runtime error because something should have been lazy, but we just put a tilde in front of it, and then it works magically. At the end, just the lessons that we learned, like Haskell really isn't scary, right? And I think this was a really big revelation for both me and my boss, the CTO, because we did this. Like he came in his first day, and I was like, hey man, we're using Haskell, and I thought he was going to run away. But we didn't have a team expert. I mean, well, Lianne was our team expert, but had no production experience. Like had done academic work, had done hobby work, but we did have a really enthusiastic team that loves to learn new languages. And so even like junior engineers were super excited to participate once we got them over the scary hump. And then just everyone was like really enjoyed it. I think the reputation Haskell has, like a really hard to use language industry, is not 100% deserved. But one anecdote that I'd like to toss in is just, I think that really, and it's a chicken and egg problem for sure, but in order to get Haskell adopted in the industry more, we need more Haskell in industry. We, I think we need to focus on like really clear code, really clear examples. And I mean, it's really hard because when you're coming at this, from Python or C or Java or whatever, a lot of the documentation and things you find online are things like this conference, right, which are fantastic and super informative, but for people who are not initiated, it's really scary and the learning curve seems impossibly high. And so like my rule is I always try to write code that like a first year kid out of grad, like post grad could actually understand. Maybe not understand the domain, but at least follow the code in a reasonable way. And so we try to stick to sort of like very simple Haskell at Kimi just because it makes it easier for people to onboard. And this is on me, but don't model Haskell after imperative code. So it leads to really bad anti-patterns. And so like one of the large thunk leaks we had was actually because I almost directly ported some Python serial handling code into Haskell, and it led to like all this crazy mutable state and trying to pass things through channels. And it really didn't work very well. And then when we kind of like burned that down and did it the Haskell way, things suddenly started working. It's actually more stable than the Python version we have, but don't tell the guy that wrote that. And then finally, just the last thing is, the team liked Haskell so much that we decided that all greenfield process development in the robotics and systems teams at Kimi is going to be in Haskell. So there will be no more Python development unless it's necessary to keep the system alive, or if it's something that just absolutely has to be in Python. So maybe something using like OpenCV or some like TensorFlow or something like that. Although both of those do have Haskell binding, so I would thoroughly encourage all the machine learning folks to get on the type wagon. And so and in fact, in the course of like deploying this, we actually developed 3 other Haskell processes, and we've been dealing with a hardware issue, and so we haven't actually deployed this main process. But things like our credit card reader are now running in Haskell, so we're literally turning Haskell into money directly. It's fantastic. So with that, here's a picture of my cat in a pirate suit. Any questions?
Yeah, I'm curious. I assume since you're using computer vision, you're actually going through and making the new key up to manufacturer standards and not how the key looks?
Correct. So, I don't want to give away any secret sauce, but basically, so what we do, we have a process called snapping, and so we look at your key and what it does. We figure out within a certain tolerance what the manufacturing code was. So all keys are typically cut to codes, and a code represents just like, if it's like 7, it's like 7 times a certain depth increment from the base of the key. And so we take that, try to clean it up a little bit, and then we generate a G-code pattern that would duplicate direct like the manufacturer tolerance. And our average tolerance, so I think the mean tolerance right now is like plus or minus 0.04 millimeters across the entire fleet. So for reference, a human hair is like 0.05 millimeters. So we're doing all right. But yeah, it's really nice because then you can kind of get around the copy of a copy of a copy problem. So we basically just wash all the error out. Cool. Anything else about keys, locks? We got it all.
RFID now.
Oh, RFID? Yeah, I used to work on RFID modems too. We can talk about that all day. Anybody? All right.